We're gonna get started because it's about 10 after. I think most everyone who's coming has probably wandered in. And we're just gonna jump right into reviewing the applications from kind of the first half of the semester. So we're just gonna review stuff from the beginning. So we're gonna start with some DiffyQ stuff. And okay, we're gonna start with the Newton's application. So just going to jump right into the problem, right? So we have sorry, let me turn the pen on. Okay, so reading the problem, we're given a bunch of information. It's 78.3 degrees outside. We're just going to say, okay, that's our ambient temperature. Going to keep reading through. Our glass of lemonade is left outside at 44.10 degrees Fahrenheit, right from the fridge. Okay, that's our why not, because right out of the fridge, this is our temperature. And then 13 minutes are going to pass, and then the drink is a different temperature at Y13, right? And then what are we going to solve for? We're going to solve for the time it takes for the drink to be 62.43 degrees Fahrenheit. And then those are kind of all listed out to the side. So these are the kind of things we want to kind of keep track of that we're going to use throughout the problem. Okay. And then the general, oh, no, okay. I'm going to write the general solution to the Newton's application is the ambient temperature plus some constant E to the RT, where R is our rate of cooling, but we don't know that yet, and we don't know our C yet. But we do know our ambient temperature, so that can be one of the first things that we plug in, right? And then that's what they do right here. So we can plug in 78.3 degrees as our ambient temperature. And then what we can do is we can use our initial conditions to solve for C, right? Because at Y naught, our T goes away and our E becomes 1. So we know at T naught is 44.10 degrees equals 78.3 plus C. And then we can solve for C is negative 34.2 degrees. So that's now another piece that we can plug back into our initial equation, right? So we're kind of just filling in these pieces as we go along. Okay, so we can plug that C in. And, okay, sorry. Do you guys prefer my handwritten or like the slides? Do you care? Okay, yeah, that's what I'm thinking too. Okay. So I'm going to plug it back in. I'm going to rewrite my equation as we have it now. 78.3 minus 34.2 e to the k t. Okay, now the only thing left to find is k, and we have some given conditions that are going to help us find that. So we're going to use that at 13 minutes, it's 53.27 degrees. So we're going to plug in our 53.27 is equal to our ambient temperature minus 34.2 e to the k is what we're solving for. And now we know t is 13 here. So we can plug this in and now we can solve for k. We can do that by dividing 78 over, so I'll do that, divided by 78.3. Nope, subtract. You're right. Skipping ahead. Thanks, guys. 53.27 minus 78.3, and that is divided by negative 34.2. And then, so we've gotten this over, we've gotten our 34 over, and then I'm going to take the natural log of both sides, right, as we're going along, to equal k to the 13. Then we can divide by 13, and that should be our k. All right, does anyone have a calculator? Because I do not. I believe it should be like 0.02. 0.024. Okay, awesome. Negative. Okay, awesome. All right, so now we have solved to be able to plug into every piece of our equation that we need. So now we have T of T equals 78.3 minus 34.2 e to the negative 0.024 t. And now we can finally answer the question, which is how long will it take for the drink to be 62.43 degrees Fahrenheit? So now we're just solving for t, which is going to be the similar procedure that we just did to solve for k. All right, so we're going to plug in all our pieces. 62.43 equals 78.3 minus 34.2 e to the negative 0.024 t. And now we're just going to rearrange everything so we can solve for t. 62.43 minus our ambient temperature divided by negative 34.2. Take the natural log of everything. Going to be equal to negative 0.024 t. I'm going to divide both sides by negative 0.024. And then we have our answer for t, which I think should be around 32 minutes. Awesome. Okay. Are there any questions about this process? Or does it kind of make sense where we get all our pieces in, where we use all the given information to find more things? Okay, awesome. So we can do another example. I'm going to have you guys try and work through most of this. This is the dead body problem, if you recall. Okay, so I'll read through it with you guys though. A dead body is found in the library with a thermostat reading 73. What is that going to be? Right, ambient temperature. You check the temperature of the body and it reads 92 degrees. What is that going to be? Right, so when we take our first measurement, that's what it is. Uh, so for this problem, okay, yeah, you're right. Oh, yeah, wait. Yeah, it is our initial condition because then we can do negative time. Yeah, we're gonna go backwards. So we're gonna say, I'm gonna start my timer when I take this measurement of 92 degrees. So that's what I'm gonna do. I'm gonna start my timer when I take this measurement of 92 degrees. Sorry, I kind of covered that up. But that's our Y or T naught, right? And then, which is usually this is what we're going to be looking for. This is at some time before the body was killed. That's what the alive body was. And then 13 minutes later, after we started our timer, the body is now at 84.3. So that's Y or T of 13. All right. So now we're going to have to solve for t, which is how many minutes before you first arrived. So this is negative time, which is why it's kind of weird. Did the murder take place? So this is going to be similar process to the problem we just did. We're going to have to flesh out our equation by solving for c and k, and then we can finally go back in and solve for t. So I'm going to let y'all have a couple minutes to work through this one. Feel free to raise your hand and ask. Yeah, and then we can roam, and if you guys have any questions, let us know.
Not for C, but for R. Yeah, that's what.
I'll do a few checks along the way. We should get a C of 19. Or is the slide wrong? Anyways. We're mumbling. Slowly reveal.
Right, that's. Yeah, that's right. That's your initial. Yeah. Wait, which you guys, so if you do the element, like 0.0 1 be They're working together.
Why are you not in your room?
They're working through this day already. I told them I was getting a drink of water. You guys did good. I told them to work together. They won't say anything.
I didn't even tell them to work together. There's just camaraderie
You
here.
You guys are. You got them right under your. But you just make sure.
Okay, what are we getting for our T? Negative 7? Is that what I'm hearing? All right, that is correct. And it's negative 7 minutes because it's negative from when we started our timer when we measured the body, right? All right. We feeling pretty good about newtons? All right. Awesome. Now we're going to move on to some of the retirement applications. Yay. Okay. Okay.
Nothing way too much fun. What are you talking about? I never was fun.
Sure.
There's a lot of our expense, that's the trick here.
Okay. Let's get started on these retirement questions. So reading through the problem, right, we have to figure out what information we can pull from the problem statement. So it says, how long will it take you to pay off a loan of $4,000 at a 5.3 annual interest rate if you make continuous payments at a rate of $64.86 per month? Okay, so reading through this problem, the amount we want to pay off is $4,000, and that's going to be our why not. So we have that there. We have our interest rate as 0.53. That's kind of our R, but we have to make sure this is annual, and our answer needs to be in months. So we're going to have to convert that in a second. And then our row is how much we put in each month, right? So we can convert that R to months, which is what we're going to do by dividing by 12. So now our R is 0.0044. I'm going to round to that. And then we have our why not in our row. Okay, so we're gonna write this as the differential equation is y prime is going to be equal to yr minus rho, I believe. Wait, yeah, it's minus. Sometimes it's plus or minus depending on the situation, right? But in this case, we're paying off our debt. Okay, so we're gonna want to solve this, right? So I think the method I'm going to choose for this one is going to be undetermined coefficients, if you guys remember how that goes. So yeah. So I'm going to start, we know the null solution is going to be the same, is going to be, sorry, is going to be our classic CE to the RT, right? Y'all remember our null solution? And then what we're going to need to find is the particular solution. So I'm going to use undetermined coefficients, right? Some particular solution is going to be, we're going to call it a variable a. And then we can take the derivative of that, which in this case is just 0. And then I can plug it back into my original equation. 0 equals yr minus p. Or, oh, and this is our particular solution still, right? Or our yp is going to be equal to r rho over r. So now we have our complete solution is our particular solution plus our null solution, and that is going to be y equals rho over r plus ce to the rt. And we actually have a lot of these pieces, right? So we can plug all those pieces in. No, not quite. YT, we're going to plug everything in, 64.86 over our rate, 44 plus CE to the 0.0044 T. And now we can solve for our C, right? By using our initial conditions. I'm going to move up to the top. We know at $4,000 we have, does anyone know what the 64.86 over our interest rate is? Okay, awesome. Thank you. Plus our C, and then the E goes away at our initial condition being 0. So now we can solve for C, which is, if anybody has that, just 4,000 minus 14,740. Okay, 740. Okay, awesome. So now we have our C, and now I can plug everything back in. And then now we're actually at a kind of similar process to the last problem we did, right? We're looking for the time that it takes to pay this off. So now our solution is I'm going to keep it in 14.7. Wait, no. Our C is negative 10,740 e to the our interest rate, and then plus 14,740. And now we can solve for t, but if we aren't given another condition that tells us this, but what are we looking for if we want our loan to be paid off? Right, so we can just solve our y of t is 0, so I'm going to move my 14,740 to the other side, divide by 1074. Oh, gotcha. Nope. Oh, 704. You are. Nope. 740. Thank you guys. Okay, we made it. Then we can take the natural log to solve for t, right? Kind of similar process to our last. and then equals e to our interest rate, or sorry, just our interest rate times t, to divide by 0.0044 is equal to our t. So how long does it take us to pay off this loan? Are y'all getting 72? Awesome. 72 months. So this is a similar process as far as solving a, first order ODE. It's just, again, picking out the information from the problem statement and knowing how to kind of rearrange and then solving for our full solution with our particular and null, and then from there plugging in all our pieces to solve for t. Are there any questions about the general process? Yeah. So our y prime is our first order ODE equation, right? If you remember all the way back, we have, this is the rate at which y is changing. And then we want to bring it back into a realm of something we can solve for, which is our y, if someone else can explain that better. Yeah.
So in this case, y prime would be, like, if this is our bank account, right? Y prime is how much is deposited or withdrawn or taken out of the account, like every month, for example. And then y in this case is our account balance. It's how much money we actually have in the account. Does that make sense?
Right. Yeah. So y prime is what is changing. Y is the current actual value. Does that kind of help? Yeah, so for our y prime equation, we can say y is our balance, and it is growing because of our interest rate, right? Sorry, our interest rate. So we can put in our initial amount and we can do nothing to it and it'll just grow because of our interest rate. But we can also add more every month. So this is our row, is we're going to be, sorry, I'm running out of room to write. We can also add monthly, right? Does that make sense where each of those pieces are coming from? So, right, y is our balance, and it grows because of our interest rate, but we can also put more in that'll push our balance to be more, and that'll become part of the balance that grows with the interest rate. So it just kind of all compounds there. Okay. If we kind of all understand this general process, we'll have you run through a similar one. This is the same one. Wait, yep. That's the final answer. Okay, this is the second one. So assume compounding and continuous payments for this problem. You charge $5,470 on your Visa. What is this going to be in our problem? Right, that's our why not. And then calculate the total amount of interest you pay after you pay off the balance at the minimum monthly payment rate of $83.92 per month, which is our row. And then this is our annual interest over here, which we want to convert to monthly. So we're going to do a similar process, and then to answer the final question, we'll have to do a step at the very end. But let's start by just solving for t like we did in the last problem. And then if you know how to go ahead and solve for the amount of interest after you pay off the balance, go ahead and do that. We can also do that all together at the end. But we're going to start by solving for the amount of months it takes to pay off this balance. Yeah, I'm not a talker.
Great.
And again, you can raise your hand if you have any questions as you work through it. Yeah.
Why is it Y?
Um, I I don't like this part of the slides, but this is the I think this might be saying this is the particular solution because this is our null solution plus the particular solution. But yeah, I think it's just supposed to be the yeah, I think it's supposed to be the particular solution. So just proceed as before.
Yes, I'll do that. My discrepancy later. Yeah, I got some. Yeah, I got 1,000. Check out this.
Okay. Okay, has anyone solved for what t is going to be when our balance is paid off? 95 months? Oh, I got 120. Okay, I like it though. Okay, so it'll take, yeah, let's run through that real quick. Okay, I'll use this blank slide. So, we can use, so, sorry. Okay, we have our, our initial, this is our initial first order differential equation. And then we know you got our null solution. To do the particular solution, I'm going to use undetermined coefficients. We remember that. You can also use like an integrating factor, mu, if you remember how to do that. We can do that in the next problem too if we want practice. Y is going to be some constant a in this case, right? We don't know what it is. You might recall like in our second order differentials, like which we'll do later, right? It could be like a sine or cosine. It's just what we think the solution should look like, some constant in this case. And then we could take the derivative so that we have enough pieces to plug back in, which in this case, because a is just a constant, it's going to be 0. And then I'm going to plug these pieces back into this equation, and I have 0 equals our particular r minus rho, which I'm going to solve for that particular solution. Wait, y particular equals r, nope, p rho over r. And then in this case, we have the numbers to plug back into that. Yeah.
We're kind of always in the first order
Mm-hmm.
equation. We'll have our general form y equals p over or rho over r equals c e to the rt.
Yeah. For these two scenarios, yeah, it's a pretty good one to just like have under your belt, just like how you can memorize like the Newton's one, we kind of just jump right into the solution that we know. Yeah, you can, this is pretty general for this one too. In the next one,
That's just for
yeah. yeah, yeah. Okay. If we got our T is 120 months. So we have our T, and then we want to figure out how much interest we paid. So we have our loan, and then we're making payments on the loan, but we're also paying interest. So we're paying more than our initial loan was, right? So what we can do is we can figure out how much did we pay total. We know we paid $83.92 per month for 120 months. So we can multiply those, 120 times 83.92, that's our monthly payment, should be how much we paid total. And if anyone has that, it should be around 10,000 something. 10,075? Okay. Okay, so that's how much we paid total. This was how much our loan was. So the everything that wasn't our loan is interest. So we can subtract our loan amount, and that'll be how much we paid in interest, which is not a great amount, if I recall correctly. A lot of interest. Yeah. So let's see. What are y'all getting for the amount we paid in interest? 4,700. Oh, 605. 605. Awesome. So you paid $4,600 in interest for your $4,500 loan. Good job. So don't do that, guys. All right. Okay. And then we have one more type of problem that we'll work through, which is a little bit different. We have, how many of you guys remember that nest egg problem? Yeah.
No.
So I'm gonna, oh my notes. Okay. Okay. Let's read through this problem. Okay. We want to retire in 40 years on a fixed income equivalent to $74,000 in today's dollars. And then over those 40 years, the inflation is an average of 4.8%. So, right, that's kind of where the in today's dollars versus future worth in 40 years kind of comes into play. How much money per month will you need to invest starting now with zero initial investment to attain the necessary nest egg for retirement if your investment pays a 13.09% yield? So the key difference between these two rates is this is our R. So this is of our total nest egg, which is some big number. We want 13.09% of that to give us $74,000 every year, right? And this is the inflation rate, which is just, I'm going to call it, let's call it, I think the slides call it L. Let's call it L. That's a fancy L, but it's bad. Okay. So that's the difference between those two. So our R is going to be the yield rate. And then we are starting with zero initial investment, so our Y naught is zero. And then we want our future value to be some big number that will give us the yield we want. Okay, so these are our knowns. Rho is the nest egg. Okay, times 40 years. Okay, so this slide kind of jumps into a big equation that I'm going to kind of help you guys figure out where all those pieces come from. Because it jumps into some kind of scary looking things, but it's actually going to be pretty similar to the last thing we did, and then we'll kind of explain where all those pieces come from at the end. So we start with the exact same ODE equals our y. This time it is plus rho though, because it's the different situation. We are growing our own accounts instead of paying off debt, right? Okay. And then as we noted before, um, our our solution is going to be same as last time, right? Where we have our c e to the rt. But this time, if you work through and solve it, because our rho sign is different, the sign in the solution is also opposite, right? And now we want to find c, but we don't know rho. So what we're actually solving for, we're actually trying to solve for rho, because remember, it's asking how much do you need to invest each month to get this nest egg? And we know from our last slides that rho is the amount that we invest each month to help build our account that's already growing with inflation. So we don't know rho. We want to solve for y, or for c, right, to kind of fill up our equation. So we're going to have to keep things in terms of rho and r to solve for c. So we can still use our initial conditions, which is 0. So 0 equals c minus, wait, sorry. Yeah, I'm going to keep this general for different situations, because say we start with a different y naught. I'm just going to keep things in terms of y naught for now. Equals c e to the rt minus rho over r. Just to show you where that big equation that we started with comes from. You might notice it'll be simpler in this problem, but I just want to show you where all those pieces come from. So we have our y naught equals, which just becomes c in this situation, right? Minus rho over r. I'm going to solve c equals our y naught plus rho over r. And then I'm going to plug this in to my equation that I already solved for. So I'm going to have y of t equals, plugging in our c, y naught plus rho over r plus, or minus rho over, wait, I know I'm missing something. E to the RT minus rho over r. And then I'm just going to rearrange this a little bit. I'm going to multiply out that e to the RT, and then I'm also going to combine the terms that have the rho over r in them, right, which is the e to the RT, and the other negative rho over r, which is going to get us e to the RT minus 1. Does that kind of make sense so far? Okay. And then I believe that gets us to the point where we have this big equation. So we can see where each of those pieces came from, right, as we solved through. We have the y naught e to the RT, the rho over the r e to the RT minus 1. So that's where the right-hand side of the equation comes from. Does that kind of track with everyone? Awesome. Whoa. Okay. Now let's see what this side means. We want $74,000 in today's money, which is our M. So we want $74,000 in today's money. And over 40 years, which is our T, that's going to grow by a certain inflation, which is where we get the e to the, I guess that was an I, e to the I T term, right? So do you guys see where all those pieces come from? So our $74,000 is going to grow over 40 years because of the interest rate. So that's that top piece. And then our bottom piece is we want to be able to pull, that's our yield, right? We want to be able to pull that much out per year. So that's where the R in the bottom comes from, right? So now we can plug in all of our pieces and solve for rho, which is how much we need to be paying each month. So we can plug in $74,000 e to the, and everything is in, right now, our time is in years and our interest rates are in years. So we're going to keep things in years for now. 0.048 over 40 years divided by 0.1309 equals, our y naught is 0, so that term's going to go away, equals rho over 0.1309 e to the 0.048 for 40 years, we already know, minus 1. And now we can solve for rho algebraically. Uh, yeah, sorry, those are parentheses. I'll make that better. Yeah, multiplied. Okay, and then someone let me know what they get for rho annually. Yeah.
Why is it 0.048?
You are correct. I made a mistake. That should be the 0.1309. Thank you for catching that. Right. So the e's are different, which is a little interesting. Okay. And so this first row we solve for will be our annual investment. Does anyone have that?
I got 2,686.
All right. And that's per year. So then our final step is just going to be to divide that by 12 to see how much we should invest per month, right? So I believe it should be around 225. That's just dollars of investment per month. Okay. Is this process kind of, is it tracking? Kind of see where we got all our pieces from and where we're going with this? Okay. Awesome. Yay. If y'all need to finish up this problem, I'll give you a couple more minutes if you want to write anything else down. Okay, and that's it for the retirement and Newton's applications. All right. I think I just put on my name tag, honestly, and then I just put the thing in my pocket.
Cool.
Yeah.
Where's the, oh, here's the pen. All right, are we ready to move on?
Yeah.
Cool. All right, now we're doing springs. Everyone's favorite second order differential equations. So here with springs, we have some sort of spring system. It has a mass, some type of dampening factor, and some innate spring constant built into the system. As you can tell from this graph, we launch the spring from 0, it goes up to some point, and then it dies back down, goes back to its original position. And what we want to find is what is that maximum displacement? Where is that highest point it reaches to? So when we look at this, first thing we see is that it is, if this will work, unforced. What does it mean if we have an unforced system? It's just going to be our linear operator. It's just going to be our y double prime, y prime, and y. We're not going to have some other function. Like in the Newtons and the retirement, we're not going to have some plus additional constant adding stuff into it. It's just going to be the natural system. Then we're told we have a spring constant. Oh my gosh. I did that wrong. How do I erase? So, oh. Oh, wow, look at that. Okay. That is magical. So then we have a spring constant of that. So that's our K value. And then we are told it is critically damped. Who remembers what critically damped means? Sorry, what was that?
The gamma value squared will be equal to 4 times the mass value times the spring constant.
Yes. So whenever we have a spring system, there is one of three different types of dampening conditions. We have critically damped, overdamped, and underdamped. So it is critically damped when this is true, critically damped. If it were overdamped, what would it be? No, overdamped. Greater than. And underdamped is when it's less than. Oh, you can't see that. Yes. Yes. So then we're also told the mass of the system. So there's our M. And then we're told it's subjected to an initial impulse of 28 meters per second. What is that telling us? Y prime, yes. At y prime of 0, we have a speed of 28 meters per second. Additionally, I don't know if it says it, I'm not seeing it, but we're starting right here at 0, 0 at the origin, so our y of 0 is also 0. All right, it's compressing the spring upward. Calculate the maximum displacement from equilibrium that the spring is compressed. Oh, here it is. Assume the equilibrium is the origin. All right, so we have our M, we have our K. We know it's critically damped, and we have our initial conditions. Now we need to set it up. So as we know, see here, we were given our M and our K, but we don't know what our gamma is. However, we know that our system is critically damped. So gamma squared equals 4mk. And we know m and k, so we can now solve for gamma as well. And when we do that, yes, it's like 400.2, right? So now we can set up our system. So when we set up our system, our differential equations look like m y double prime plus gamma y prime plus k y, and it's unforced, so the right-hand side is going to be 0. Does that make sense? Okay, now we want to actually go through and solve this problem. Since we have an unforced system, what is our particular solution? Particular. 0. There's no forcing function, so our particular solution is 0, which means all we need to take care of is our null solution. And does anyone remember for second order differential equations how we usually do our null solution?
Is it the C1, the root 1 t plus C2 e to the root 2t, but in this case it's going to be C2 e to the, no, C2 times t e to the.
So first off, yes, that's right. That is what we end up with. But where do we get our R1 and R2? I started to hear it. Characteristic polynomial. And our characteristic polynomial comes from our linear operator. Our y double prime becomes r squared. Our single prime becomes r, and our y goes away. And then we can do quadratic formula in order to solve for our r's. And yep, I heard it. Inside this parentheses, we have our gamma squared minus 4mk, which we already determined from critical dampening that gamma squared equals 4mk. So this inside the square root is 0. So our r is just going to be minus gamma over 2m, which with our 400.2 and our m, what does that come out to be? 2.08, is that? 2.1 what? Okay, 2.129. Okay, so now going back to right here, we have our yn equals c1 plus r1t plus c2 e to the r2t, but we only have one root. So we can't use the form exactly like that because we have some resonance inside of our system. So what happens when we have resonance? How does this null solution change? Yes.
The C1.
You pick up a T right there. All right. Now we're able to use our initial conditions in order to solve for C1 and C2. I'm pretty sure that's what. Yeah, this slide goes through finding our C1 and C2. So I'll go back a little bit just so I have more space over here. So when we plug in 0 for T, what happens to our null solution? We just get C1 because right here, this second term is multiplied by a T. So when we plug in 0 for T, this whole term goes away. And that's equal to our initial condition. What was our y of 0? 0. Yay, that helps make our lives a little bit easier. Because now I'm just going to rewrite our y as our c2te to the rt. Now we still need to find that other c, and so how we're going to do that is we need to take the derivative, and we have two functions multiplied together, so we have to use our good friend the product rule. Oh, I accidentally clicked something. And so when we do product rule, we're going to get c2 e to the rt plus r c2 te to the rt. Then we plug in 0 for t. And what happens when we plug in 0 for t? C2. Just like we did with our y1 over here, this term has a t in it. So when we plug in 0, we have just C2. And what was it was 28. From our initial conditions. So now we have solved for y. But what was the problem originally asking for? Max displacement, so we're not done yet. Yes, max displacement, this is back to your Calc 1 days. You find a maximum when your derivative is equal to 0. So all we need to do, we take our y equals 28t e to the minus 2.1, what was it, 9t? We take the derivative, 129. Thank you. All right, we take the derivative. Again, we use product rule. Oh, I'm a mess over here. Then we're going to do minus 2.129 times our 28 TE minus 2.129 T. And that's our derivative. And again, we're just now setting that equal to 0. And when we set that equal to 0, both of these terms have our e to the minus 2.129t. So that can be pulled out. And e to the power is never 0, which means we can divide by e, both sides by e to the minus 2.129t and cancel it out. So now we just have 28 minus 2.129 times 28t equals 0. So we're going to add that over. 28 equals 2.129 times 28t. So t is just 1 over 2.129.
Yeah.
Which is, does someone have that? 4 point. All right. So now we found the time it takes to reach that maximum displacement, but we want to find the actual displacement. So all we need to do is go back and plug that in for t into our original equation, and we get y equals 28 times 0.4697 e to the minus 2.129 times 0.4697. And what do we get when we plug that in? Sorry, say that again. 4.84 meters. And that is the solution. Does that process make sense? Does anyone have any questions about that? Yes. What happened to the E? So right down here at this step, we set it, since it was set equal to 0, we divided both sides by that E. So there's another way of writing it. Whoop. Oh, keep doing that. I forgot the 2. All right, and then 0 divided by E is 0. So then we're just left with the thing on the inside. Cool? Any other questions about this process? No? Cool, because now we have another one. But this one's still unforced. We have a spring constant of 10. This time, instead of telling us it's critically damped, it tells us it is underdamped. And it gives us the dampening. And it also gives us the mass. It stretches to equilibrium. From this position, you pull the spring downward 1 meter. So what is that telling us? Our y naught is not 0 in this problem. Our y naught is -1. And then we release it with an upwards velocity of 21 meters per second. Calculate the maximum displacement. All right. I'll go ahead and let you guys try to attempt this one on your own. It's going to be a little bit different than the last one because it's underdamped, but use the same type of process up until you're actually assembling the solution, and then we'll walk through it together in just a moment. course. Have a good one. So for this one, we do our characteristic polynomial, just like the first one. However, don't we all? All right, we have a minus 36 inside that square root.
Sold out. No, it gets so hurt you realize. I'm pretty sure you saw him work the man.
Whoa.
Yeah.
I am moving this keyboard out of the way. All right. So this time we have complex roots. R1 is minus 1 plus 3i. And R2 is minus 1 minus 3i. But that's okay because we still know that our solution looks like C1e to the R1t plus C2e to the R2t. And so we're just going to go ahead and directly plug in. Now, if I were to distribute that t through and split it up into the multiplication of e's, both of those terms would have an e to the minus t. Here, I'll write it. So we can rewrite this as e to the minus t times c1e to the 3it plus c2e to the minus 3it. Now, what's our favorite thing to do when we have an e to the it? Euler's formula. But this is okay because if you remember in class, we talked about that when we have a C1e to the 3it or some it plus C2e to its complex conjugate power, we can take a little shortcut. And that shortcut is essentially we still have our e to the minus t out front. But if we were to go through and turn it into Euler's formula, you can do that if you want. I'm not going to. You'd find that C1 and C2 are complex conjugates of each other, which means your i's are all going to go away, just like all our problems. And you get a C3 cosine of that 3t plus a C4 sine of that 3t. We now no longer have any imaginary, so there's nothing to fear. Does that make sense how we made that jump?
C3 and C4 are not necessarily complex development.
No, C3 and C4 are real numbers. That is the nice thing about this is since C1 and C2 are complex conjugates of each other, we end up getting rid of all of our imaginary parts, which makes sense because your spring actually exists. Yes.
And don't we only worry about cosines, sines the imaginary section of it? Or am I?
No, we still have to take into account the sign here. Yes.
That go away because it was like an odd function.
Um,
So it's like a -3 IT.
yeah. So because we have the 3 to the IT and the -3 IT, one of them's going to have both cosine and I sine will be positive, and one of them, the cosine would be positive, the I sine would be negative. And then the complex conjugates of C1 and C2 end up making it all nice and pretty and gets rid of any negatives. Any other questions? Okay, so now we have our solution y, but yet again, that is not what we are here for. We are to keep going. Oh. Okay, so now we want to use our initial conditions. So first we'll use this one. So y of 0. What happens when e is raised to the power of 0? 1. And what is cosine of 0?
Just kidding.
No, we got C3. What's sine of 0? 0. And so all we're left is our C3
What?
equals -1. All right. Now we have C3, but we still want to find out what our C4 is. So we're going to take the derivative. Once again, our good friend, the product rule, needs to step in. And when we do this, we get a minus C3 sine. Oh, we pick up a 3 out front too. All right, everyone agree that that's the derivative? All right. So now we plug in 0 for t yet again. For this portion, we have a minus sign out front. And what happens to our cosine? 1. So we just get minus C3 out of that. And for this portion, this time this part will go away. So we're left with plus 3C4. And we set that equal to 21. And we already determined that C3 was -1. Therefore, C4 is 20 over 3. All right, so now we have solved y, but yet again, that is still not quite what we're here for. So we take our derivative. And we're going to set that equal to 0. And we want to solve for t, which is kind of gross. But since this is an application, we can use our calculators. Except unless you're in the final. But when we do that, let's see. Oh, that's not right. Does it say? I don't think it has the solution on here. Is anyone able to plug that in and solve? Let's see, we can get rid of our e to the minus t's. So we'd have 21 cosine 3t plus 29 over 3 sine of 3t. So that's what we need to solve for 0. I divided by the e to the minus t and distributed. Oh, this is slightly wrong. That would be 11, I think. Pulled in this negative. That's positive. That's now a minus. And then I have a 3 sine minus a 20 over 3 sine. So that's going to be a minus 11. And then we have a 1 cosine plus a 20 cosine. So then we get 21 cosine 3t plus or minus 11 thirds sine 3t. So 21 cosine 3t equals 11 thirds sine 3t. So we can do 62 over 11 equals sine 3t over cosine 3t. What is sine over cosine? Tangent. Excuse me. Then I'm running out of room. We have 3t equals inverse tangent of 62 over 11, which means t equals 1/3 inverse tangent is 62 over 11. Anyone have that?
It'd be 6.
21 times 2.
Yes, you're right.
And that needs to be a gradient. When we take an inverse tangent, it needs to be a gradient.
Yes. We're going to do radians.
Then you have to divide it by 3.
Yep. 0.466. All right. We finally got our time. So now still not done. Then we have minus cosine 3, 0.466 plus 20 over 3 sine of 3, 0.466. All right. Now, does anyone have a solution for that?
You store a y.
Yeah. That's it. I have it written up there at the top. We have our y equals e to the minus 0.466 times minus cosine of 3 times 0.466 plus 20 over 3 sine of 3 times 0.466.
That's a nasty problem.
You can go give us this exact problem test. 100%. It would be the only.
Considering this part down here where you'd have to do an inverse tangent, and I don't know about you guys, but I know I can't do an inverse tangent just off the top of my head without a calculator. So one thing that maybe he could ask is have you solve all the way to here and have answer choices of what the t might be, since that doesn't require 4 point what? 4.01 meters. All right, we got the answer. Woo! Aren't you so glad that we went through that? Any questions about this process? You good? This is the last part of springs for this review. Any? Sorry? There aren't any in your application homework at least. So, okay. How do I bunnies? Do I have to escape out of this?
No one look at my tabs.
It's thinking.
It's thinking really hard.
Just like me.
Hello? Ma'am?
Hello. Okay.
I receive it.
Look at all the stuff you already did.
Wow, it's a miracle. Woo! You guys are so smart solving all of this so quickly.
Process, I can calm you down, that doesn't mean So I'll probably back.
Okay. Okay, bunnies, chapter 3. So the whole idea behind chapter 3 with bunnies was that not all of our differential equations are going to be nice linear functions. And so sometimes we just need to find the fixed points of our nonlinear differential equations and analyze the system around those points. So, bunnies is chapter 3. So here we are considering two species. Oh, it's red now. With the what? On here. Oh, look at that. I'm learning so many things right now. I hope you guys are too. Okay, consider two species, X and Y, that grow logistically. The equations for growth rate with the species competing for each other are modeled by these equations. And we want to know what is the limit of species X as time goes on further and further and further. This is all given in a very long problem statement. Oh, yes, sorry. Oh, yeah, I think. Oh, I lost my mic. Just a second. Yes, I think that is an error. We're just going to ignore that. All right. And then, yes.
So we're just solving for like the fixed point, where like where like two are stable. It's like
Yes.
fixed point.
Yes, because you're going to have a couple fixed points in these systems. But can you see that one of them is going to be the trivial fixed point? Because we're multiplying by an x right here and a y out here in front. Obviously, both equations will be 0 when x and y are equal to 0. So we want to find the non-trivial fixed point for when we actually have species and we just, instead of saying both of them are dead. Okay, so now here we're, after a long problem statement, we're given A equals 10, B equals 5, R1 equals 1, K1 equals 35, C equals 6, D equals 12, R2 equals 1, K2 equals 390, and we're also giving our starting points. Usually this problem gives you the phase portrait as well. And when you look at the phase portrait, this is going to be so bad. It's like all moving into a spot here, which means we only have one fixed point, one non-trivial fixed point that's not on the axes where this is. And since our initial conditions right here are inside of this plane somewhere, it means we're going to be attracted to that fixed point. So we just need to plug in these values, we get x prime equals R1 is 1, K1 is 350, A is 10, B is 5, R2 is 1, K2 is 390, C is 6, and D is 12. Oh, forgot my Y. All right, so again, we're looking for fixed points, which means these are equal to 0. And again, we want to ignore the trivial fixed point, so we're just going to ignore these things. So now we have 2 equations and 2 unknowns. I'm going to go ahead and move our x's and y's over to the other side. Yes, because we're looking for the non-trivial. And these x and y, yeah, exactly. Those don't help us. So we're just going to ignore those. So we have 350 equals 10x plus y. That comes from this equation. And 390 equals 6x plus 12y. That is my plan. I love linear algebra, so we're going to solve this using linear algebra. You could do substitution, elimination, all that elementary stuff, or you can set up a superior matrix. And all we need to do is find x and y, which means all we need to do is find the inverse of this guy. And an inverse of a 2 by 2 is nicer, yes. Yes, you could. You could. So, yeah. So, first, we'll do my favorite method, which is finding the inverse. So, xy equals, if we take the inverse first, we need to find the determinant. So, the determinant is equal to 120. So, that's 10 times the 12 minus 5 times 6, 90.
Didn't we get, oh, we don't have -10.
And so it's going to be 1 over the determinant. Then we take our matrix, we swap the diagonals, and we make our off diagonals negative. And now we multiply that out. And when we multiply that out, what do we get? Anyone have it? Sorry, say that again. 20. All right. So then our answer of what is the limit as t approaches infinity for x is 25. Does that make sense? So that's how you do it, by finding the inverse. You can also do this using Gauss-Jordan elimination. And how that works is, again, we go back to this step where we have our matrix times our xy. And all we're going to do is we're going to set up the matrix, but this time we're going to augment it with our vector over here. Oh. Now we're just going to essentially do reduced row echelon form. And when we get this left-hand side to the identity, we'll have the solution over on this side. That's just another way to solve this. Yeah. So when asked to go over the Gauss-Jordan elimination. And
No, it's a different, that's separate.
oh, sorry. That's the answer. There we go. This is I had to do this in my recitation earlier today as well. This is something different.
There's a wall.
Okay. Does that make sense? Any questions about that process? Pretty straightforward compared to the springs that we just did. Sorry? 25 is the answer. Yep.
Can't trust it anymore, can you?
All right. Now we'll do the second problem for bunnies as well. Consider two plants, Stinkius arsicus, plant A, and Intoxicus bellissimo, plant B, that live right next to each other and are modeled by these equations. Suppose that plant B is more sensitive to the presence of plant A than A is to B, so that kappa B equals 3 kappa A. What must kappa B be so that we can have a 50-50 mix? So what does it mean if we have a 50-50 mix of the two species? Yes. So what does that, how do we numerically or express that? Yes. A is equal to B. And then we also know that kappa B is equal to 3 kappa A. Then we have these two equations right here. We set them equal to 0. We will have 4 equations for unknowns. I like how this one, you can tell the difference between the K and the kappa, because that is usually the most confusing thing on this problem.
That's so real though.
So since both these equations are set equal to 0, can't we just ignore these parts out front? Oh my goodness. Yep, so now we can use these two equations up here to substitute in, so then both of our equations are only in terms of two variables. So I'll substitute just arbitrarily. I'll call all my A's B. And just because I don't want to deal with fractions yet, I'm going to use substitute kappa B equals 3 kappa A.
I bet you this one.
Oh, no doubt.
Yeah, exactly. It's like totally.
It does look traumatizing.
So now what I'm going to do is I'm going to solve these equations in terms of B, so I can just set them equal to each other. So this one, we can pull out a B out of these two terms, and we subtract over the Ka, so we get minus Ka divided by 3 kappa A minus 1. I did a lot of steps right there all at once, so I subtracted kappa A over to the 0, and then I pulled out a B out of these two middle terms, and then it's 3 kappa A minus 1 times B, so then I just divided that over. And then down here, I'm also just going to rearrange for B, and that's going to get minus KB over kappa A minus 1. Mm-hmm.
How can we have bottom A, kappa A, kappa A times B?
These come from two different equations. So this one comes from there, that one comes from there.
stuff at the
Okay.
top.
So now I'm just going to set these two equal to each other. So we're going to have minus Ka over 3 kappa A minus 1 equals minus Kb over kappa A minus 1. I'm going to multiply both sides by each denominator so that we just get rid of all our fractions. Sorry, those aren't equal. Okay, now all we need to do is rearrange in order to solve for our kappa. So I'm going to move this one over to this side. I'm going to subtract this Ka over to that side. So I get 3 Kb kappa A minus Ka kappa A is equal to, I'm running out of room. I'll move over here, sorry. I write big, I run out of room. It's a tragedy of life. So then we have over here Kb minus Ka. Did I get that right? So now kappa A is 3 Kb minus Ka equals Kb minus Ka. Therefore, kappa A is equal to Kb minus Ka over 3 Kb minus Ka. And we know Kb and we know Ka, so we can know kappa A. And then we're looking for kappa B, so all we need to do is multiply this by 3, and we have kappa B. Now just plug in these values for our K's. This is A, this is B. And what do we get when we plug those in? Sorry. Was someone saying it?
Is there a difference? You have differences in K and kappa.
Yes, K and kappa are different. Yes, that is, I think, the hardest part of this problem. Is differentiating between your kappa and your K. So you have Kb minus Ka over 3 Kb minus Ka, which this is Ka, this is Kb down here.
I think kappa B.
0.45.
Why did we multiply the to the?
Because up here, one of our equations that we are given, where was it given? Right here, was that kappa B is equal to 3 kappa A. Yeah, distinguishing those kappas and Ks, that's what's going to kill you in this problem, quite genuinely. Like, as you can see, like, going through solving this problem isn't too bad. It's just differentiating those Ks and kappas. If you are scared of making that mistake, create your own variable for it so that you don't get them confused. Does that problem make sense? Any last questions about that? Yes. It's because of the way that this equation is built. The fact that our r's are out front, when we set it equal to 0, we just end up getting rid of them. For this specific type of a logistic problem, that's usually going to be the case if you're solving your kappas. But if you're asked a different type of question, it might change it. Make sense? All right, that's bunnies. Woo!
It's working on it. Woo! You guys are ready? Now I know this whole time you guys have been thinking, wow, you know what? I really miss linear algebra. Well, guess what?
I know I did.
You get to do it again. I'm gonna go over the animation applications once I get to the right slide. Ha! Oh, spoiler alert. Woo! Okay, so these ones are pretty chill. So it says a rotation about a point in space requires combining yada yada yada, honestly. With the given points, which are these points over here. Oh no, I don't want that color. That's the color of the devil. Sorry. Rotating negative pi halves in space. What matrix does these operations for the set of the blue points where the points are down there, essentially? So when talking about what we need to do to rotate these points around their own center, our first problem is that if we look at a little graph, and these are our points, not actually, but pretend. If we apply this rotation matrix, which we're given right now, it's going to rotate it about this point right here. It's going to rotate it this way, and that's not what we want. We want it to rotate along its own center, which is like somewhere in here, right? So then the first thing we need to do is move all of these individual points so that this center is now at the origin, so we can apply this rotation matrix, right? But to know how much we need to move the center to get it to the origin, first we need to know where the origin, where our center is, right? So the first thing we're going to do is average all of these points so we know what the center is between them, right? So we'll take our x is going to be 1 plus 5 plus 6 over 3, and then our y is going to be 1 plus 2 plus 6 over 3. And that'll give us the x and y coordinates of the center of all of these points, right? So that's 12 divided by 3 is 4. And then 3 plus 6 is 9 divided by 3 is 3. Yeah? So that is the center of all of our points. So now we need to figure out how a matrix such that when I multiply any given point, we get, actually, I'm going to say it this way. We need a matrix such that when I multiply my center of points, 4, 3, and then 1, I'll talk about that in a second, I get the origin 0, 0, and then 1. So to talk about this thing right here, because it is kind of weird, like why do we have that 1 there? One way to think about it is that when we rotate things, we're moving them in the x and y plane, but we're rotating them about the z-axis. So if you think about the way that we talk about moments and rotation, like in statics and dynamics and things like that, our rotation vectors are in the k direction, right? It's a similar thing. In this case, z is not changing, z is constant, but z is still present because that's the axis we're rotating about. If that helps you understand it, use that. If not, just look at the fact that we have a 3 by 3 and we need to have something in the bottom to multiply it by a 3 by 3. That also works.
Um, okay, perfect. So I'm going to start with the identity matrix and then build it up from there, like that. Okay, so now if I multiply these points by my identity matrix, this 4 is going to multiply by this one, and my y is going to multiply by, sorry, you can't see, y is going to multiply by that one, right? So that means that changing here, these ones will scale my x and y coordinates, right? But then if I put a number in over here on these terms, for example, my top coordinate here would be 4 plus 0 times 3, which is 0, plus whatever I put in this spot times 1, right? So that's why I'm going to put my translation into these two spots. Now, what do I need to put in these two spots so that I can move the point 4, 3 into 0, 0? -4 and -3. Perfect. Okay, so that is my first matrix done. All right, but I have to set up in total 3 matrices. But I'm going to call this my translation number 1. Okay. But next we just have our rotation matrix. Our total one is going to look like that. This is what our whole thing is going to look like. So we have our translation 1. Our rotation matrix, we're going to just plug in the theta that we're trying to rotate into this equation over here. So my rotation matrix is going to look like the cosine of -π-halves, and then the negative sine of -π-halves, and then 0, and then sine of -π-halves, and then cosine of -π-halves, and then 0, 0, 0, 1. Sweet. Once we plug everything in, we get the cosine of -π-halves, which is the same thing as -90 degrees, is 0. And then the negative sine of -π-halves, -π-halves takes me down to here, right? Which is going to be -1, but then because it's negative sign, it becomes +1, 0. This is going to be -1, 0, 0, 0, 0, 1. Okay, perfect. So now I have my rotation matrix. And then my T2, my second translation matrix, now that we've moved all of our points so they're centered about the z-axis and we've rotated them, now we need to translate them back to where we started. So we're just going to take our original translation matrix, and how are we going to move everything back? Yep. And that's it. So now our total, one thing that I see some people get tripped up about is the order of these does matter, because the order that we multiply matrices in matters, right? So we have to set it up so we're working this way. So we start here and then work that way, multiplying that way, right? So our total matrix, I'm just going to call it capital M, is going to be equal to this guy multiplied by this guy multiplied by this guy. Perfect. And as far as multiplying these matrices go, you can, for example, like multiply these two together, get a 3 by 3 matrix, and then multiply that matrix by this matrix. Or you can like do these two and then this, like do these two and then multiply this one. You just have to make sure you're keeping the right sides together. And similarly, you can multiply all these, get one massive matrix, and then multiply it by our original point to translate it. Or you can multiply the point here, and then there, and that also works. Does anyone have any questions?
about how this all works? Yeah? Peach? Awesome. I'm gonna have you guys try one then. Or actually, do you want me to go through the like actual multiplication of all three of these matrices? No? Okay, awesome. I won't then. I don't want to either. So it's a very similar problem. You're just doing it clockwise with pi thirds. And these are your points. See if you can set up your matrices. Start working it out. We'll be walking around to help you out. Let's see. What's the sine cosine of pi thirds? I don't remember. Do you remember? I don't remember.
Sine, cosine is 1/2. Sine is the other one. Okay. I think, right? Because 1/2 is bigger than the square root of
3/2.
3/2. No, is the square root of 3/2 bigger than 1/2? The square root of 3 is greater than 1.
I don't remember.
Yeah, because I think it's swapped. Because I just always remember like cosine is the longer one on pi over 3.
I think between this negative switched between slides.
Oh, that's a good point. It's because we're now moving clockwise. But I should say that. I'm pretty sure.
Yeah, you could put it in the matrix, or you could just do negative pi thirds, right? So that work either way.
I think so. I think it works out to the same. I don't know.
But then the cosine did it.
Well,
Shouldn't
okay.
those be negative?
If we plug it in,
The sign's the exact
just-
same. with it.
yeah, that makes sense.
Yeah.
But I mean, yeah,
Is it the same?
that's what I'm trying to
the
figure
same
out.
Or is it different on the previous slide?
It is different. The negative sign does move. And I think that is because if you think about it, the cosine will be the same at negative pi thirds or positive pi thirds,
Oh yeah.
but the sign will be different. Just a little note about the formula that's used on this slide. So if you guys compare this rotation matrix with the one from the last slide, the negative sign moved from that sign to that sign. So that's because we're moving clockwise. So you can either like use this matrix and then just plug in pi thirds, or you can plug in negative pi thirds and have the negative up there. You see what I'm saying? Okay. All right. Sweet. I'm just gonna show them the solution. Thanks. Hello? All right. Yeah, it gets gross. But that's the basics of how it works. If you have any questions, please ask. But we're about at time, so I just thought I'd go ahead. Yeah, of course. Huh?
Where do you get those shoelaces?
Amazon.
Is there like that size?
No, I don't know. Maybe actually.
But we are recording this
Or can we get the
to
slide?
go on YouTube.
Because they have all the solutions on
We're
them.
not supposed to leave those or distribute one of the solutions, but we thought of
There's a video that has solutions.
Hey, listen, man. I just work here.
Then you give it to us and we don't give it to them.
give you blank slides.
Do we have blank slides?
This will be so much easier just to these ones.
I don't know either.
Doesn't make sense if you guys are just.
Uh-huh.
It's hard. Can't get slides.
We can give you blank slides. You can look at the solution on YouTube.
This is on YouTube.
Will be.
Going to be.
We don't know how quickly or how long it will take to get uploaded. I hope not. The hope, I think, is that we get this uploaded soon. I'm going to send out announcements to my recitations. I'm sure Mia will do the same.
So Mia recorded this one, right?
Huh?
Mia recorded this one?
Yes,
Yeah.
so we're recording it through the AMLAC. So I think it's going to get uploaded. The AMLAC has their own YouTube channel.
Okay,
So I think it's going to get uploaded there. Sorry?
Never mind. I'll answer your question for me.
Yeah.
It's all good. All right.
Okay, thank you guys. See ya.